Okay, so I know this says honors. You know, as of right now and the way we're trying to do things, this is all simply concept. Okay, so the concepts that we would do in each class are the same, all right? Especially in waves. It's not heavily mathematically, it's not the way I do it. So you're gonna notice that it says honors, but I'm gonna use this for both classes. All right, so in this video and in this PowerPoint, there's gonna be some review. All right, there's some things I didn't say in the first one, but let's move through it. So, superposition. I already mentioned this part down here, that when waves go through each other, they react with each other, and then they move out looking exactly the same as before. All right? So the law of superposition or superposition principle basically says when those waves come together, how do we figure out what it looks like when they're together? So I already mentioned in the other video how when we have two crests, they would come together, they would increase amplitude, and then they go through. And that's constructive interference. If we had a wave coming in like this, underneath, cancel out, and then go through. So superposition, the law and the principle, what if it wasn't like a crest of 1 and a trough of -1? You know, when they come together, they cancel out. How about if we had a crest of 1 and a trough of like -0.5? So 1 and then a half, but negative. When they come together, what would result is just a half. Okay, so 1 plus a -0.5 would be a +0.5. So you would still have a little bit of like a dimple, a little bit of a crest, but it wouldn't be totally flattened out. All right, and I would get more into that in class, but for now, that's good enough. Remember, they pass through looking the same on the outside. We already did constructive. A little extra note here is in phase. I know it's on the last worksheet that was due, and that's fine if you didn't have it. But in phase basically means they look the same, right? And they're canceling, or they're adding up. And now the other one, there's our, we already had that. Destructive interference, we call it out of phase. All right, so out of phase, you're just out of order if you think about that. One's high, one's low, cancel each other out, come out on the other side looking the same. We already did that. All right, interference patterns. So if you go to a swimming pool or out in a pond, everybody's throwing a rock into a pool of water or into a pond or a river or something. And you see that forms these ripples. So let's imagine we have our fingers and we're going like this and making ripples in the water. They're creating these circular patterns like this. When those waves interact with each other, you see like these gray lines that form. You probably could see it at the beginning of the PowerPoint. I think it was over in the other corner, where they almost look like gray. And those are places of destructive interference. So the crest from one is hitting the trough from another, and they're canceling out. And then the dark and light ones are just places where two crests or two troughs hit. It's constructive. Let's see if I can picture up here. There we go. So it's kind of hard to see, but you can definitely see the dark and the light spots. But it's kind of grayish through here. I'm sure you can find better pictures online of this. All right, reflection of waves. We would try to use a ripple tank or show this in class somehow, where you have kind of like flat waves, or basically if you take a block of wood that's flat and you just went like this and it created a nice flat wave. That's one type, and then you have point source waves where you're just hitting water with like your finger and it's creating these round waves. So what happens when those things hit barriers, okay? I'm not gonna worry too much about that, but I will say this, when any wave hits the corner of a barrier, so if we have a corner like this, even if it's a flat wave or it's a round wave coming in, it's gonna reflect as a point source wave on the edge of that barrier, on the point. Okay, go and write those down. So this is kind of hard to show. Let's imagine we have this pole, obviously, and we have a string attached to it. And let's say that string will not move. And I go like this and I make a wave. That wave will come in and it'll come back the other way. So it will reflect the opposite direction. All right? That's for a stationary barrier. Right here, stationary barrier. So crest would flip into a trough. Okay. Now, when you have a non-stationary barrier, and this is kind of odd, I don't know how often you would see this, but let's say you tie a circle, a fairly big circle, and when I do the string, that circle is able to go up and down this rod. Basically, if the wave came in like this, it would come up and it would come looking the exact same on its way back. So stationary barrier flips, non-stationary, it comes back on the same side. So here I come, crest, whoop, whoop, comes back as a crest. All right. We're getting into a little bit of sound stuff here, okay? And in the video I want you to watch, there's going to be demonstrations about sound. And one involved holding a rod. I don't know if you could hear that, the different sounds. That one's not vibrating much at all. All right, but everything vibrates with a natural frequency. If you ever played a baseball or softball and it's cold out, you would definitely feel vibrations in your hands. It'll probably hurt your hands if you don't hit the barrel of the bat. But no matter what we're talking about, whether it's a glass or like a wine glass or like a cup or a metal rod or a table, everything vibrates with a natural frequency, okay? When we think of a natural frequency, we could think of this. If we had slow motion and we slowed things down, ever hear or see somebody go like this with their finger around the top of a glass and it starts to vibrate? They're matching the natural frequency. And that's what this is talking about right here. I'm not going to get out the big the boxes that you'd see in another video. I just have my tuning forks here. And so, I don't know if you can hear this. That's 256 hertz. On a tuning fork, it tells you the frequency right on there. And we have different kinds, 320. So, I don't know if you can hear that. So 256 has a lower sound, a lower pitch we call it. 320 would have a higher pitch. We go up to 384, 512. And one way I like to do it too is, I don't know if I could do it here, put it on the table. When you touch it to the table, you're vibrating more atoms, doesn't matter what it is, and you get more sound, right? So if I have two tuning forks that are exactly the same, you can do this. And I hit one. Don't touch it. I could hear this one. It's not very loud, but I could hear it. Okay. So what happens is we have this forced vibration. Okay? It's actually not really a forced vibration. A forced vibration is more when I hit the tuning fork and then I touch the table, and you're forcing it to vibrate. Right? Or I take the tuning fork and I just hit it off the striker here. Okay? Resonance is the last thing I showed. So when you match the natural frequency of an object, so you have your little brother or sister, they're on a swing and they're swinging back and forth. You don't push them when they're coming back. You wait until they're all the way back and then you push them, and then their amplitude gets bigger and bigger and bigger, and that's an example of resonance. Okay, so if you've ever heard about a speaker or a person like an opera singer singing, ah, and can they break like a glass? They can. Okay, there's this awesome video on YouTube of this this blonde-haired kid, and he tries to do it, and he breaks it, and he's yelling, "Mom, Mom, I did it!" So that can't happen, and that's called resonance. And when resonance occurs, and you match that frequency, the amplitudes will get bigger and bigger. So that wine glass, or whatever he's holding, is going like this. And if you're matching that frequency, the amplitude's going to get bigger and bigger until the structure will break. Okay? When I match the natural frequency of these tuning forks, that's too loud, that's too loud. The other one starts to vibrate. You say, well, they're not touching, but the air, the compression and the stretch of the air that's going over is hitting it and causing it to vibrate. Okay? If I do two separate ones, this is a 320, this is a 256, even though they're kind of close, you hear nothing. They have to be the same exact frequency. All right, standing waves. Standing waves are basically waves that sort of like don't look like they're moving. So we try to do demonstrations of this. If you have a person over here holding, like, let's say a slinky, and you're holding over here and you're going like this, waving it back and forth, all right? The first fundamental would be a half a wavelength. So we get it, it just look like this. It'd be like this. And so the points that are moving the most are called antinodes, and the points that are not moving or look like they're not moving are called nodes, N-O-D-E-S. So you notice that this is one half of a wavelength, this is one wavelength, 3 halves or 1 1/2, and then this is 1, 2, okay? 2 wavelengths. So standing waves occur at every 1/2 wavelength. If we look at the blue line as, let's say, being the one that is going this way, and the purple or pink, whatever that is, line is the one going this way, okay? Now, if we have these waves coming down, being reflected, okay? And you're still producing waves over here. So here we go. This one hits, comes back, as another one's being produced. Cancel. And that's what happens right there. So these nodes here, 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 which occur at every 1/2 wavelength, that's a place of destructive interference. Okay, that's everything I just said. Oh, and they're known as harmonics. L meaning the length, and remember 3 halves, that's just 1 1/2. This is the symbol for wavelength. All right, and that's it for now. I'm going to start getting into sound. Already did a little bit. It's easy to talk about resonance when we're talking about sound. If you're in class, we do these demonstrations where you can kind of see the standing waves and the resonance that's produced.